Okay, so this is problem set 8. There are just 4 problems here. The first one is the main one. We'll spend most of our time working on the first one. This is interesting Stokes calculation. Okay, so here's the model. Okay, we know that in linear acoustics, this is all linear, right? Small amplitude acoustics. We've seen the relationship, the pressure condensation relationship. And it's just this without this term, okay? So imagine this being gone. You'll probably recognize that. It's something we've dealt with before. So Stokes modified it, and I don't know his motivation. It could have been attenuation of a sound wave. And this is going to cause attenuation when we introduce this. And we'll see this explicitly here. But you know it's coming because this is the classic relaxation. What's going to happen here is that, and this is the first thing we'll investigate, is when you subject a fluid to an instantaneous increase in pressure, the condensation will lag behind. Okay, and it's going to lag behind by this characteristic time here. Tau, relaxation time. So I don't know if you can see that in here. We've built up some experience with this, but we're going to prove it. We're going to prove it, and it's straightforward. And because of that lagging, that will introduce. That's going to cause an attenuation of a sound wave. Now it's a reasonable. I want to point out that this is a reasonable model. If I've got a gas here or fluid in general, I think, and I imagine, subjecting it to an abrupt pressure change, but again, not too abrupt, right? We don't want to generate shock waves. That takes us beyond the linear level. If we generate a pressure change here, it's reasonable to think that the condensation will lag behind because of inertia. So it's a reasonable model. So I guess the next question is, why don't we include it in our basic theory for acoustics? It's not in there, right? We've been dealing with our basic acoustic model from the textbook. We just have this, we've assumed that this is not there. So my guess is that this is probably a really small compared to thermoviscous losses. That's my guess, but I don't know. And I've never thought about it until right now, to be honest with you. I should have thought about it a long time ago, but it is interesting and it seems physical. So let's explore it. So as we discussed in lecture today, when you see an equation like this, which looks like classic relaxation, you can easily check that by considering the special case where you abruptly change this. So we're going to do that at time t is equal to 0. At negative times, we will. Is this what they ask us to do? We should really take this to be some non-zero, this p to be some non-zero to be physical, but it's not going to make any difference. And is that what they tell us? Now that I'm thinking about this.
Which doesn't increase from 0
All right, from 0 to p. Okay, it's just making the calculation a little easier. This is not a fundamental, we're not losing anything fundamentally here. So let's just do what they say. So we'll assume that this p is 0, and then at time t is equal to 0, you can imagine that we abruptly increase it to some positive value. So it's going to look like this. And the question is, what does the condensation do? Okay, and the information is going to be in this differential equation here. So let me rewrite it here, a little slightly different form. We're solving for S here, so I'm going to put that on the left side of the equation. So this is a first order differential equation. This we think of as a derived term. It's non-homogeneous or inhomogeneous. It doesn't involve S. So this is a typical derive, and we can think of it as a derive here. So we need to solve. We're going to solve for positive times here. For positive times, the right-hand side is this capital P divided by rho naught c squared. So we need to find the solution here. We need to solve this subject to the initial condition that S is equal to 0. Because for negative times here, with p's being 0, s will be 0. All right? So that's the mathematically setting this up. This is a simple first-order differential equation. It's going to have a homogeneous solution. When the drive, we think of this as a drive. Mathematicians call it call this the homogeneous equation. This is an inhomogeneity here, whatever. But in physics, and engineering, we think of this as a drive. With this being 0, the solution of this is trivial. You can do this in your head, just this decaying exponential, and you can verify that that works here. So that's the homogeneous solution. We need a particular solution. Okay, and in physics we call that what? I don't know if you guys I don't think we encountered it this quarter, but you should have encountered it last quarter. Mathematicians call it the particular solution. That's going to be what solves with this driver. We call it the steady state solution, a solution that's valid for a long time. They're all transients have died away. So I'm sticking with the math language here, but they have there's physics aspects to it. So the particular solution here, you can get this by inspection. If I want to solve this now, this is a constant, okay? So you'll recognize here that just mathematically and also physically, that if we choose s to be a constant, this will be 0, then s just has to be that. So we can really get the particular solution here just by inspection. It's going to be that. So I add the two to get the general solution. Here's the homogeneous solution, which contains one independent quantity, one independent constant that we're free to set to any value we want to. Okay, the particular solution has no freedom. It is unique. It's given by this. We just have one constant here because it's a first-order differential equation. The typical case where you have a second-order differential equation, there'll be two constants, but there's just one here. So this is the general solution for this differential equation. Now we fix the constant by demanding that it have this initial value right here. So at t is equal to 0, so we get just 1 here. We demand that this equals 0. That means a has to be. There's no choice here. It's unique. Has to be given by this. We plug it back into our solution, simplify it a little bit, and here is the solution for the condensation. And it's classic relaxation, right? You can see that it's initially s is 0 for negative times, and initially at time t is equal to 0. And then, because of this abrupt change, the system relaxes to this new equilibrium state where it's constant here. And it relaxes exponentially fast. And the characteristic time is this tau. So that's the relaxation time. Okay, any questions about that? Okay, so next is probably, we're going to look at acoustics, I think. Better follow what they say here. So now we have, instead of this constant capital P, we're going to have harmonically, sinusoidally oscillating in time. And the way we're going to approach this, following what they say here, is this. Remember now, the square of the speed of sound is how the pressure changes with density, adiabatically, right? So this P here, the dP is just the acoustic, that's just the acoustic pressure. The change in density here is just going to be the condensation times rho naught, because the condensation is the fractional change in density. So we can replace this c squared with this, okay? Now, because we're going to have a phase difference, because of the relaxation process here, we're going to have a phase difference between the pressure and the condensation. That's the whole point of the model here. Our C becomes complex. And you know what that means. That's the way we mathematically are going to be able to get at the attenuation. So I'm going to put a bar underneath here. We now recognize these as complex. I'm not going to bother to put a bar under everything. We understand these are complex and there's a phase difference between them. So it's going to force a complex C. But I need to distinguish this, and you can see why. Here's our differential equation. This is not complex. This is the actual speed of sound. Okay? It's not complex. So we need to be a little careful here. It's the it's going to be the low frequency or quasi-static speed of sound. So why do I have this? Why is it the low frequency in this case? Because when omega tau is much less than 1, this is what we mean by low frequency here. What kind of a lag do I have in the condensation compared to the pressure? No lag. Okay? So there we have a real speed of sound. Okay, so we put in an e to the I. We're assuming everything's going like e to the I omega t here. Okay, you can imagine that we're imposing a pressure wave on there that's actually in this problem we actually don't have to think of a wave, do we? Yeah, we're going to get there. Okay, so for this time-varying pressure here, everything's going like e to the I omega t. We substitute that in here. And the time derivative is just going to bring down an I omega t. So we get this. Okay. And now we're going to use this. The square of the complex speed of sound is the ratio of these two things with their complex values. We found the pressure. We substitute that in the numerator. In the denominator, we just leave the s. The s's cancel here. And you can see that we get the rows cancel, and we get that the square of the complex speed of sound is the square of the low frequency real speed of sound times 1 plus I omega t. Take the square root, and you get this, and there's our complex speed of sound. And we know how to get attenuation from this. The imaginary part is going to specify the attenuation of the wave. The real part of this will tell you how the phase velocity changes. And it'll change here because of that square root. You can see that it's going to change. I don't think we're asked to do that. So part C is... Oh, so now we're going to prove the attenuation. We know this is coming, but this is just another proof of this from a slightly different perspective. Here's our linearized Euler's equation, F equals ma. And for harmonic variation, I replace the time derivative with I omega. Here's our linearized equation of continuity. Okay. And I replace the time derivative, and I get this. Okay. Now, how do we want to beat this down to one equation and one unknown. This is the usual idea behind any wave equation for any system, not just acoustics. Typically you have these different variables, and you want to eliminate all of them except one and get an equation, which is going to be some kind of wave equation. So I'm going to, first of all, get rid of S in terms of P, because we're going to go for P here, so I get rid of S. And now you see I have two equations here. The two unknowns, P and U. We're going to get rid of U. So to do that, we've been through this kind of thing before, and it was even on a quiz, right? It's so important, I put it on a quiz. We're going to take clearly the divergence of the top equation here. When I take the divergence here, and I see the divergence here, if I can eliminate the divergence of U between those two equations, right? So it's just simple algebra. So I said subtract from the continuity law. I see what I did. Okay. So the best thing to do is take the divergence of each side of the equation here, put the I omega rho naught on the other side of the equation. And now, if you look at this equation and this equation, if I just subtract them, subtract the left sides and subtract the right sides, I'm going to eliminate the divergence of U. And when we do that, we get this equation. And now we can beat this into a standard form here with the Laplacian of the pressure. Bring it over here. Be careful with the i's, okay? And this will end up being a plus. And there'll be a p here. And the coefficient of the p here is, you can see from here, is omega squared over the complex c squared. All right? We call this, we define this to be the complex wave number, and we get the standard Helmholtz type equation. Except now, this is it's not real, it's complex. And we've seen this before, of course, in this chapter. So the complex K is omega over the complex C. Here's the complex C. And now we could analyze this exactly. I don't know what, I can't remember what they ask you to do. I'm just going a little bit beyond what they... Okay, so this is a... this is going to be a lossy Helmholtz equation because this is complex. But let's verify that. And they don't really tell us what to do here, but I'm going to assume a short relaxation time. So the attenuation is weak here. That's going to make the math a lot easier. So, and we've actually been through this before, I think, in lecture. So the square root of 1 plus a small quantity is 1 plus 1/2 that quantity. And then, 1 over 1 plus a small quantity is approximately 1 minus a small quantity, our standard approximations. So we get this. And now we can identify here. Our K is going to have a real part minus an imaginary part. We put the minus in there because we know this is, because this is going to attenuate. There's no way that there's going to be gain here. That would be a real interesting trick, right? How can we, where's that energy going to come from? Right? We don't have any mechanism here. So this is going to be attenuation in this case. So you can see here, when you equate these, look at the real parts. The real parts equal to this. You'll notice here that in this I lied. Well, I didn't lie. Way back here I mentioned, somewhere here, I mentioned that this is going to give us, in general, this gives you not just attenuation from the imaginary part, but for K. Maybe I mentioned it here, I can't remember. Well, anyway, in general, as we saw today in lecture, this can be a function of frequency, okay? And so that the attenuation here causes dispersion. In this particular case, however, you can see that it's for the low frequency limit, it's not there. We just get the usual relationship. There's no dispersion here in the low frequency limit. So before, when I was talking about this, somewhere up there, I was thinking of the exact solution. If you do the exact solution, if you don't make the approximations here, and if you're interested, please do this, and let me know what you find. You're going to find, I'm almost certain, that this is going to become frequency dependent. You'll introduce dispersion here. It's, however, in realistic systems, it's typically very weak in acoustics. And the important thing here is in this, and what we find if you just identify the imaginary part, we find we've got an absorption coefficient. There's our absorption coefficient. And you'll notice that there it is. It's proportional to the square of the frequency, which always seems to be the case in the low frequency limit, the elephant thing. And it depends upon the relaxation time. If you zero out the relaxation time, you have no relaxation process. You're not going to have any losses. Alpha is equal to 0. So it's interesting. I don't know the history, but it's interesting that Stokes did this. And apparently it's negligible because we don't, we're a long way now into describing the absorption of sound. And this is not in we've been flirting with this kind of different perspectives and homework problems. But it's not in our model. I don't think it's in there. And the model works well, as you will see. Well, you started to see with carbon dioxide. And the big point about Monday's lecture is going to be what we really care about, air and water. And there's a lot more surprises to come, incidentally. The carbon dioxide was already surprising, but there's more to come. Okay, is there any questions about this? Okay, so that's the interesting problem. The rest of these are just kind of simple problems. Let's look at 834. So here's the idea of 834. We have show that the intensity of a traveling wave is, so we have an attenuating traveling wave here, okay? We know, this was a previous homework problem, that the intensity is what you would naively expect. You just take this pressure and take the amplitude here, substitute it in the p squared over 2 rho naught c, the usual thing that we establish for the intensity for waves that don't attenuate. And we get this, and it gets doubled because it's p squared. This is what you'd expect. And again, the amazing thing, and we did this in a problem last week, is that it's only accurate to first order in the absorptions, for small absorption, that's a surprise, I think. Okay, so we have this. And now, so I just said this, okay? And you may remember this. So now we're supposed to look at how the intensity changes in space here. So if we differentiate the intensity with respect to time, you can see that we're going to get the intensity back, and then there's a factor of minus 2i. Okay? Now you can look at, one way of looking at this is you can bring this I on the other side of the equation, and now you have this. And this has a physical meaning here. It's the fractional rate of change of intensity. It's the rate of change of intensity divided by the intensity. So it's going to be the fractional rate of change of the intensity. And we find that it's a constant. So I can integrate this, right? That's going to be a straight line. How does the intensity, how does the, I don't want to integrate this. I'll just leave me, because I got this I here. I don't forget I said that, okay? We can see here that the fractional rate of change of intensity is a negative constant. It's a negative constant. And does that sound familiar? Remember the dB? This is just a slightly different perspective on dBs. Okay, the dB measure here, or the intensity level. And to see that, you'll notice that we can write this fractional rate of change of density. We can bring this I in there if we make this a logarithm, right? Because the derivative of this logarithm is, going by the chain rule, is going to be the derivative of the log, which is 1 over I, and then di dx. And this is proportional to the intensity level, the logarithm of the intensity. So we see here that because this is a straight line of negative slope, this is going to be the intensity level is going to be a straight line. And we already established that in lecture. That's why people like to deal with dB here. So many dB per meter. The intensity level is falling off linearly with space. So that's very convenient. It's going to look like this as a function of x. And you might say, what happens when it hits here? Is there any problem when it hits the axis? Do we have to go to 0? Is this 0? No, this is a logarithmic scale. Where's 0? It's infinitely far down there. So there's no problem with the axis here. And let me do this. This zero intensity level here is whatever, is any reference you want to call it, there's no physical significance to it. There's an x here. Okay, so it's a moderately interesting problem. It's not, a lot. I remember going through these, looking at these problems. Some of them there's a lot of problems here. A lot of them I just didn't find to be that useful or interesting. So sometimes you struggle to find problems that you want to assign. But this one has, it connects with the intensity level, so I think but it's very simple. As is the next one, 4.3. Calculate so this is just plug and chug, as they call it. So we're going to find the relaxation time for heat conduction, thermal flow, in air at standard conditions, and compare to the relaxation time for the viscosity. This turns out to be interesting, as I'll point out to you. So we have a formula for the relaxation time due to heat flow, due to thermal conduction. Here it is. This is the thermal conductivity kappa, heat capacity at constant pressure. So for air, we think of rho naught c squared as rho naught c times c. It's the easy way because it's hard, everybody now remembers this, okay? In fact, I think they remember it too well because some students, I don't know if it was any of you guys, but I remember at least one distance learning lab report. They used 343 as the speed of sound for the Helmholtz resonator experiment. Was that and that wasn't the temperature when Jay took the data. Yeah, you want to be careful about that. Now, maybe it's negligible, I don't know. But, this is at room temperature. This is at room temperature, which is defined to be 20 degrees Celsius, okay? And of course, this is the wave impedance, right, 450. So we plug the numbers in. You can look this up in the back of the book, Appendix A10. And we get this number here. It's, again, as we pointed out in lecture, a very small number here. So, and we'll explore that smallness in a minute. I can see here. What about the relaxation time for shear viscosity? So we zero out the bulk viscosity. It's typically 0. Here's the formula. Plug the numbers in, and look at this. Now, what do you think about that? So you guys probably haven't had, have any of you had any what's called kinetic theory of gases? It's using mechanics and approximations, a lot of approximations, to get at transport properties, to get at quantities like the viscosity. Now, we didn't talk about this, but you should suspect that if somebody knows what's going on, if you really know what's going on in your system, you should be able to derive what the coefficient of viscosity is. You shouldn't think of it as some empirical quantity. You can think of it empirically, but we know the source of viscosity in a fluid. It's actually what we call a transport property. Remember this system here? It shows it very well. If I have a plate, a fixed plate here, and I'm moving this plate, let's say constant velocity, and I have a fluid in here, the velocity profile, you remember, the particles up here have to be moving with the, right on here, the surface here, are going to be moving with the plate here. And then there's this profile here, it's a linear profile, going down to 0. So this is the ordered velocity. Here, there's this profile. The particles, on the average, have 0 velocity next to this fixed plate and the same velocity as this plate, whatever it may be up here. And it varies in between like this. And the thing here, what gives rise to viscosity, the fact that there's some friction here, is the fact that in addition to this ordered motion, there's this random motion, because this is at some finite temperature T. And these particles will drift. They'll migrate around here. And the particles that stuck here, they'll come and stick for a while, then they'll leave. So a particle coming from down here has less momentum here than it's going to have once it sticks to the plate. And where does that new momentum come from? It comes from the external agent that's pulling this thing. That's why there's a frictional force. So given that we know what's causing the friction here, we should be able to calculate this. And you can do it with kinetic theory. okay? And typically in classes, there's a lot of you make a lot of approximations. This is in like Schroeder's book. You guys take any? See, we used to have a thermal course, but I think it's gone. It's been combined with the stat mech course. You guys take that, or are you gonna?
We spent like a day on kinetic theory. It was
God, really? That's too
maybe
bad.
even a whole day.
Okay, well, I'm going to tell you what you're missing. Okay. Now, I haven't worked this out, but I look at this and I say, see, kinetic theory is approximate. There's only, to do Newton's laws on Avogadro's number of particles, you're going to make approximations. There's no question about it. And typically, especially at the educational level, there's approximations are pretty strong. In the past, in the 1800s, when they had nothing else to do because they didn't have quantum mechanics and relativity, they beat kinetic theory to death. They did all kinds of, it got very complicated. You just don't want to look at that. Nobody looks at that stuff anymore, okay? And one of the reasons they did that was they couldn't explain specific heat observations. There were these errors. They were big. So the first thing they try to do with some of these people, it's a natural human thing to do is, well, we just need to improve our kinetic theory. So we're going to go in there and crank out, more detailed calculations. And it didn't work, okay? They didn't come close. The problem is that there was something fundamentally new going on, okay? But anyway, getting back to kinetic theory with all these approximations, my suspicion here is that using kinetic theory for a gas, we should be able to calculate formulas for, well, I know you can do this. You can find, from this expression here, you can calculate the thermal conductivity. That's something you can find, okay? So we should be able to not rely on these empirical values here. Whoops, I did something. Okay, here we're relying on these tabulated values of the thermal conductivity and the viscosity. There are expressions from approximate expressions from kinetic theory. My guess is when you plug those in, they're going to be the same because they're so close, right? So the point I'm trying to make is I suspect there's some kind of physics going on here. That these two things are approximately the same. There's a reason here. They're fundamentally tied together. Why are they tied together? Because of diffusion. The fact that diffusion is involved in viscosity, and it's obviously, it's involved in thermal conductivity too. So, but I haven't pursued this, but it's just suspicious when you see these things being close like that. The other thing we can look at here to make this to drag this problem out and make it more interesting is this relaxation time. It seems pretty small, doesn't it? Okay, so what we can do is, we know we're going to get the greatest attenuation when omega tau is equal to 1, right? So that's going to force a certain frequency. What's that frequency? Well, it's easy to find. I solve for omega here. I divide by 2 pi to get the actual frequency, and I get 800 megahertz. Okay, so we're in air, right? That seems like a pretty high frequency. Well, how high is it? Well, I don't know how to answer. The only way I can appreciate this is I can find the wavelengths. Easy, right? The wavelength is 0.43 microns. Okay. Now, you can calculate or look up the mean free path for air. So we got these air molecules, nitrogen and oxygen, doesn't really matter. We just got these air particles. Let's think of them as air particles. And they're colliding. The average distance they go between collisions is, at room temperature and atmospheric pressure, is 0.068 microns. Okay. Incidentally, this mean free path is something you can calculate from kinetic theory. Okay. You can estimate it. So you'll see here. What do you see here? So we're roughly an order of magnitude. The wavelength here is not down to the mean free path, but it's getting there. And what does that mean? What happens when the wavelength of sound is so small that it's getting near the mean free path? The fluid description breaks down. It's starting to break down here. And by the fluid description, I mean the continuum, treating the fluid as a continuum, neglecting the fact that you've got these particles in here. So you have to go to a completely different, a very different description. It's much more difficult. So we're getting there here, this frequency, but it's still, our fluid description will still be roughly right, even at this very high frequency here. And the attenuation will be great, you know, because that's where omega, the attenuation will be strong there. Okay, any questions about that one? Okay, the next is also a plug-in. And this is the last problem. It's 5.2, the Prandtl number. Now, the Prandtl number is important for us because here's its definition. And this happens to be dimensionless. And you may want, you know, if you didn't know much fluid dynamics or acoustics, you'd wonder, okay, it's dimensionless, so what? Well, the importance behind this is if you go back and look at our absorption coefficients, if you take the ratio of the absorption coefficient due to viscosity divided by the absorption coefficient due to thermal conductivity, and you make approximations, neglect the 4/3, I think there's going to be a 4/3 in there and a gamma -1, they're all of order unity, you get this. So the importance of the Prandtl number here is that it gives you roughly the ratio for acoustics, but it's a general thing in fluid dynamics. This is why fluid dynamics, even if they're not doing acoustics, they may want to know, you know, do I have to worry about thermal conductivity here? What's the thermal conductivity compared to the viscosity? For example, the losses due to that, whatever. You look at the Prandtl number. When the Prandtl number is large, viscosity is dominating. The effects of viscosity dominates the effects of thermal conductivity. And when it's small, it's the other way around, okay? If it's roughly on the order of unity, then you've got to deal with both. So this is why this is an important thing, standard fluid dynamics approach. Fluid dynamics is so complicated that anytime you can simplify what's going on, you do it. People don't hesitate. Okay, so let's find the Prandtl number for air. We just looked this up in the back of the book, and look at that. It's interesting. It's close to 1, right? So the effects of the attenuation due to viscosity and thermal conductivity are roughly the same. You can't neglect one over the other. For hydrogen, I think they said helium in the book, but helium's not tabulated in the back, so I think it should be hydrogen. It's this. And now, what am I about to say about these two numbers? Yeah, so there's some physics here, and it's kinetic theory. My guess is kinetic theory will tell you that the Prandtl number, this is a big statement. I don't know if I want to make this, but it's suggesting that the Prandtl number, I don't know if I can, I really feel hesitant to say this, but it looks like, don't tell anybody I said this, okay? It's on videotape. That it looks like the Prandtl number for, for a certain temperature, like room temperature and atmospheric pressure, it looks like it's independent of the gas. That's a very strong statement. That's like a universal kind of statement. But I didn't realize that until right now, but that's what we would be going for here. If we looked, the fact that these, within the context of the approximate kinetic theory, it looks like these are probably going to be shown to be the same, which means it's going to be the same for all gas, approximately. And it's a good thing to know, because sometimes all you care about is approximations. And you can get physics out of this. If you want to be really precise, then you got to deal with these differences here. But from to appreciate what's going on, it looks like at a fixed temperature and pressure, this is the way it looks, okay? At a fixed temperature and pressure, all gases have the same Prandtl number. Okay, I'm going to have to, I'll have to look into this. And I know the person to ask. That's interesting. I don't recall that coming out of kinetic. Well, usually in kinetic theory, from teaching point of view, we don't get that deep into it. We never get to the Prandtl number. But it looks like this ratio may be independent of the. I don't know. I feel really funny about that.
If you calculated it for oxygen, it'd be pretty close to that as well.
Uh-huh.
Based on the numbers that I talked about.
Yeah, so clearly the next step here is to, look in some books on kinetic theory and that go a little bit beyond the book we use here, Schroeder's book. Have you guys used Schroeder? Do you know what I'm talking about? Oh, okay. It's a thermal physics book. It has thermodynamics and statistical mechanics. The idea there is thermodynamics is a very empirical subject. And I can eat up the whole time very easily, you can tell. But anyway, I won't, I promise. But thermodynamics is a very empirical subject. You really can't derive, you assume constants that are empirically determined. If you want to be able to derive those and go at a deeper level, that's statistical mechanics. The problem is that statistical mechanics can only deal with relatively simple systems. So thermodynamics is still important and it always will be, I think. But those now are typically united into one course, an undergraduate, upper division kind of course called thermal physics. And the book that we use here is by Schroeder. I'm surprised none of you, okay, Mark's, okay, yeah. And it's not a bad book. I think it's a pretty good book. Yeah. So that's what I'm going to crack open first, although it won't get at the Prandtl number, but I might be able to see something. I'll probably just pose it to another professor who's more knowledgeable about this than I am. It's a lot easier doing it that way. Or I can just look it up on the internet, but you never know what you're going to find on the internet. So whether it's going to be there or whether or not it's going to be right. Could be. It may be okay. I do it all the time. Everybody does it, right? But you need to be aware that it may not be right. Okay, anybody have any questions? Okay, so we'll continue with this material, like I said this morning. One more lecture, one more problem set, and then there'll be the quiz on the chapter. Yeah.
Next week, Friday, we don't have any class, so for
yeah. Thursdays, I guess, as far as the federal government goes, Thursday's a holiday, but Friday's not. Well, all I can tell you is this is like a university.
Well,
We don't have. No, I'm not. I mean, I'll be here because I'm here every day, right? But I don't think you'll see a lot of classes going on.
Well, the students are told to be at 96-hour liberty.
I'm sorry. Say that again.
96 hours of liberty, so we don't have time.
Yeah, we were given a Friday off by the university already.
Oh, okay. Yeah. So,
Well,
yeah.
that's